Thank you all for attending the presentations in this session. Today, I will discuss the ADME of siRNA GalNAc conjugates. A little bit about my background. I've worked in the industry in the area of drug metabolism and pharmacokinetics for the past 20 years. I spent the largest portion of my career at GSK in a group dedicated to understanding the mechanisms of DDI, with the bulk of my experience in small molecule late-stage development. I started work with Alnylam initially as a consultant in 2017 and then as a permanent employee in 2018 in the DMPK group. I was fortunate enough to be involved with the NDA filing and approval of the first siRNA for the treatment of amyloidosis. So let me give you an overview of the content I'll be discussing. I mentioned that the bulk of my experience was in small molecule development. When I first came to Alnylam, I was surprised and quite excited by the uniqueness of the mechanism of action. I was also surprised as to the uniqueness of siRNA disposition patterns, and that is what I'd like to share today, specifically GalNAc-siRNAs. Most of my work is in the non-clinical area, so the majority of my talk will focus on rat and monkey disposition. At Alnylam, we have an extensive platform that is exclusively devoted to delivering RNAi therapeutics. I will review GalNAc absorption and PK, GalNAc tissue distribution, GalNAc metabolism, GalNAc excretion, GalNAc DDI profiles, and this has had a tremendous impact on labeling and key decision-making criteria for the need for clinical evaluation. And finally, I'll give some GalNAc PKPD insights. siRNAs are relatively large, approximately 16 kilodalton, negatively charged molecules, and therefore do not easily cross plasma membranes, so functional delivery is a challenge. Alnylam's first product was a siRNA encapsulated lipid nanoparticle, or LNP. We have demonstrated that LNPs can be used to effectively and safely deliver RNAi therapeutics to the liver. However, IV infusion may not be ideal in certain settings and for certain indications. Also, multiple excipients in the LNP formulation can complicate the development of LNP-formulated siRNAs. Therefore, we also developed an alternative approach, GalNAc conjugates, which are administered subcutaneously and consist of a single chemical entity. This approach constitutes the majority of our late-stage clinical pipeline, and for the purposes of this talk, I'll focus on our GalNAc liver targeting strategies. Our GalNAc siRNAs are designed for liver-specific delivery. A GalNAc ligand binds to the Aschia-glycoprotein receptor that is uniquely and highly expressed on the surface of hepatocytes with high turnover rates and is conserved across species. Our siRNAs are also linked to a trivalent N-acetylgalactosamine, or GalNAc ligand, that has a high receptor affinity and specificity. It is metabolically stable in plasma and has favorable safety and CMC properties. These characteristics of our conjugates allow for targeted and efficient delivery of GalNAc siRNAs to hepatocytes. Following endocytosis and endosomal escape, siRNAs are loaded into the RISC complex and mediate target messenger RNA knockdown. GalNAc siRNAs are administered by subcutaneous injection. With good aqueous solubility, GalNAc siRNAs quickly enter systemic circulation, mostly via the blood, where they are efficiently distributed to the liver via ASGPR uptake. In the liver, siRNAs are mostly metabolized via hydrolysis and biliary excretion represents a minimal pathway for elimination. A small amount of unchanged siRNA is eliminated in the urine, with metabolites constituting a larger amount in the urine. GalNAc-siRNAs have unique absorption profiles compared to small molecules or biologics. As an illustration, here are some key plasma PK parameters for vutrisiran across species. In general, there is low plasma exposure due to targeted rapid liver uptake. Tmax generally occurs quickly in about 1 to 2 hours in rats and monkeys and about 4 hours in humans. Plasma half-life is also short, 1 to 2 hours in monkeys and approximately 5 hours in humans. In general, the pharmacokinetics is conserved across species, scaled by allometry. As mentioned before, plasma exposure is driven by rapid liver uptake. To understand this further, we dosed siRNA compounds, one with a GalNAc and one with no GalNAc. As you can see, the GalNAc facilitates liver uptake, and plasma exposure is considerably greater in the absence of liver-targeted delivery. Route of administration influences the plasma profile as well. As an example, here is one siRNA compound in rat and monkey administered intravenously and subcutaneously. As you can see, the intravenous route of administration results in a profile with a shorter plasma exposure. In contrast, subcutaneous administration of lumasiran results in a slow absorption from the subcutaneous injection site and facilitates efficient hepatic drug uptake without saturation of the ASGPR receptor. There's also a dramatic difference in liver PK, confirming the target liver delivery in both rat and monkey. As shown here, the plasma PK has a short half-life, about 3 to 8 hours. In contrast, the liver half-life is substantially prolonged, 120 to 150 hours. Overall, liver exposure is substantially higher as well, about 6,000-fold compared to plasma. To elucidate the clearance mechanisms of a drug and its metabolite via metabolism and/or excretion, a radiolabel study is generally a regulatory expectation, both non-clinically and clinically in humans. Regulatory agencies have waived human ADME study in light of sustained radiation exposure expected due to long residence time of GalNAc-siRNAs in the liver. So the rat QWBA is extremely important. So far, we have conducted radiolabel studies with 5 GalNAc conjugates, 3 using tritium, which I will share today. Now, with our molecules, there are a number of challenges. Where do we place the label? Which monomer do we pick? We have 2 strands. Which strand do we follow? What about the linker on the sense strand? Intrinsically, this experiment ends up being compromised, and we had to make some choices. We decided to label non-native monomer 2' fluoro and middle position so that we can track as long as possible. The studies were set up generally the same for each compound and typical for a rat radiolabel study, with the exception of an extended sampling time for the intact rats. Bile duct cannulated rats were restricted to 7 days because of the cannula. Urine, bile, and feces were collected to measure excretory routes, and a QWBA was performed to establish tissue distribution over time. All 3 compounds had similar profiles with good recovery of 80+%. There was a negligible amount of radioactivity remaining in the carcass, suggesting there was complete elimination. Also notable was that fecal recovery of radioactivity was small relative to recovery of that in urine. The QWBA data shows rapid distribution to the liver with a Tmax around 4 to 6 hours. It also shows the specificity of liver targeting, as few other organs show significant levels of radioactivity. Notably, kidney is another organ with significant radioactivity, but liver to kidney ratio in concentration is approximately 30-fold. As a percent of dose, the liver has greater than 100-fold radioactivity compared to kidney. You'll also notice a prolonged amount of radioactivity through 336 hours. By 1344 hours, however, the radioactivity is close to the limit of detection. GalNAc-siRNAs contain terminal phosphorothioate linkages and are fully modified on the 2' position of the ribose and 2' O-methyl and 2' fluoro modifications to enhance metabolic stability and duration of effect. Nevertheless, their structure is composed of a series of oligonucleotides that, although relatively stable, are metabolized by exonucleases, which chop off nucleotides from the end, and endonucleases, which cleave internally. These enzymes are ubiquitously distributed in plasma and tissue and show little cross-species difference in metabolism. The AsN-1 3' metabolite is generally the major metabolite in all matrices. It is pharmacologically active and monitored in both clinical and non-clinical studies. Most metabolites only are present in liver, but not in plasma. Generally, there is cross-species similarity in metabolism profiles. GalNAc moieties are very stable in plasma. Their short half-life is due to efficient liver uptake. Sense strand to antisense strand in plasma is 1-to-1, but in liver, intact sense strand is almost undetectable, as the sense strand is quickly cleaved after uptake into hepatocytes. The linkers are metabolized via hydrolysis of the amide bonds. GalNAc-siRNAs are minimally excreted in the urine. In rat, the largest portion of radioactivity, approximately 53 to 68%, was recovered in the urine. However, overall renal excretion for unchanged parent across compounds is low, constituting less than 25% of the dose. This pattern is also reflected across species, including human, indicating renal elimination of unchanged siRNAs is minimal. A closer look at the biliary excretion showed total radioactivity recovered in feces in the intact rat was lower than the total radioactivity excreted in bile in the bile duct cannulated rat. This suggests there may be reabsorption of radioactivity via intrahepatic recycling. Interestingly, the radioactivity in the bile constituted mostly parent and an N-1 metabolite. However, in feces, there was a negligible amount of either parent or metabolite. Consistent with the intrahepatic recycling, the plasma profile of total radioactivity shows a classic double peak. At these extended time points, there was no parent or AsN-1 3' metabolite detected in the plasma. These data indicate the full length and AsN-1 3' metabolite are further cleaved in the GI tract to shortmers and get reabsorbed. The mechanism of biliary excretion is likely exocytosis, as opposed to transporter involvement. An advanced ESC GalNAc-siRNA conjugate was labeled with Alexa 488 on the 5' end of the sense strand. Primary hepatocytes expressing ASGPR were incubated with 10 nanomolar of the labeled siRNA in green for 4 hours before addition of lysopaner in red to the media. Cells were imaged 15 minutes after addition of lysopaner. Given the precedence of biliary excretion through lysosomal exocytosis for large molecules and the evidence of siRNAs to accumulate in lysosomes, the most likely mechanism of hepatobiliary excretion for siRNAs is lysosomal exocytosis. Understanding drug-drug interactions are an important aspect to drug development, but the guidance documents and body of literature were largely driven by small molecules. So what kind of DDI strategy is appropriate for siRNAs? Overall, mechanistically, siRNA DDIs seem unlikely. They are relatively large, metabolically stable, with limited tissue distribution. However, there is limited data to definitively rule out an interaction with CYPs and transporters. And since this was a first-in-class therapeutic, there was an unknown regulatory expectation. Of course, over the course of 5 or so years, we've had the opportunity to collect DDI data across 12 different programs, and that formed the basis of a retrospective analysis that has allowed a shift in the amount of DDI data needed. This was recently published by Diane Ramsden in 2019. The data collected characterized a variety of GalNAc-siRNAs as CYP substrates, CYP inhibitors, CYP inducers, transporter substrates, and transporter inhibitors. The totality of data confirms that chemical inhibition or induction of drug metabolizing enzymes and transporters mediated by GalNAc-siRNAs is highly unlikely. The phys-chem properties of siRNAs likely makes physical interaction with CYP enzymes and transporters less likely. The potential for pharmacologically mediated DDI should be evaluated by understanding the mechanism of action and downstream or upstream effects of a target gene knockdown. In general, based on this data set, in the absence of any pathway-mediated DDI potential, it can be concluded that GalNAc-siRNAs are unlikely to be a victim or perpetrator of DDIs, and in vitro or clinical investigations are not warranted as a standard work package. This in turn should save needed resource and streamline development for additional siRNA therapeutics. Liver PK is the primary driver for siRNA pharmacodynamics. As shown here, following a single subcutaneous dose of a GalNAc-siRNA, the siRNA concentrations were measured in plasma in blue and liver in red, up to 42 days post-dose. The y-axis on the left side is siRNA concentration. As a measure of target engagement, the siRNA bound to the RISC complex in green was also measured. Complementary to the liver PK and the RISC binding was the plasma biomarker, demonstrating that the pharmacodynamic effect in purple with the y-axis on the right side of the graph. This data explains the prolonged pharmacodynamic effect relative to the short plasma half-life and the long liver half-life. Compilation of PK data of GalNAc-siRNA conjugates across monkey, rat, and human has given important cross-platform insight. Monkey and rat liver exposure is similar across the platform. This is important since liver PK is the primary driver of pharmacodynamics. Likewise, human plasma exposure is also similar across the platform. These trends are likely due to the similar metabolic stability of GalNAc-siRNA conjugates in plasma and liver. Only GalNAc-siRNA conjugates with adequate stability were advanced to further development. Additionally, all GalNAc-siRNA conjugates contain the same delivery handle, resulting in selective and efficient liver uptake via ASGPR. This allows for interspecies PK scaling through allometry. In summary, following subcutaneous injection, there is complete bioavailability of GalNAc-siRNA. GalNAc-siRNA and metabolites require greater than 1 month to be cleared in rats after subcutaneous administration time. Time to clear is likely to be longer in human. GalNAc-siRNA are primarily eliminated by metabolism with a minor contribution from renal excretion. The AsN-1 3' is the primary active metabolite, and it is also eliminated by metabolism to shortmers, and metabolite profiles of siRNA is similar across species. Clinically relevant DDI potential of GalNAc-siRNA conjugates is low. Good correlation is found between exposure and dose in rat, monkey, and human, providing predictable in vivo disposition of GalNAc-siRNA conjugates. There are many people involved in this research. I tried to capture as many individuals as possible. Those that I miss in the Alnylam Early Development Group and RNAi platform team, I'm lumping together and extending my warm welcome and thanks for them. I appreciate the opportunity to share this information and thank you very much for your attention.